A Roman bishop sits by the window of his episcopal residence on the North African coast. Late afternoon has settled over the town. Beyond him, the Mediterranean catches the last light of the day, and waves fold onto the shore, leaving the sand in scattered, shapeless ridges. Soon the sun will disappear. Lamps will have to be lit if he is to keep working. The man is Augustine of Hippo, theologian, philosopher, and later a saint, whose surviving writings amount to roughly 5 million words. He wishes the warm gold outside his window could last. Perhaps time might simply stop. Perhaps it could even reverse. But what would a reversed world actually look like? The sun rising over the horizon would not seem especially strange. It might resemble an ordinary dawn. Everything else, though, would become deeply unsettling. The breakers striking the beach would need to gather themselves back together. Droplets would lift from the shore, converge, and form unstable towers of water before drawing away toward the sea. To Augustine, such a sight would appear to defy the natural order established by God. The thought is disturbing enough that he turns from it. Then another possibility takes hold. What if time could be seen stretched out in front of him, proceeding without pause from one instant into the next? The sea would continue hammering the coastline. It would move toward the busy settlement until his own home became rubble mixed with sand. As ink falls from his quill onto parchment, he imagines time advancing through everything, spoiling all it touches, and spreading an inescapable disorder. The human world of the present would collapse into meaningless heaps. The flourishing world of nature would eventually wither into dust carried on the wind. Above, stars would vanish one after another, until no lights remained in the sky by which the passage of moments could even be marked. Once there was nothing left for time to consume, would that ravenous force finally come to an end as well? What is time, then, if it is not the unavoidable growth of disorder? What is it, if not the destruction of God's ordered universe until all that remains is an endless accumulation of sand? Augustine pulls himself away from this dark, waking vision. Outside, the light really is fading. In the final traces of sunset, he takes a breath and writes the last words of his day. What, then, is time? Had he been able to look far ahead and examine the ideas of modern scholars, Augustine might have found his bleak intuition unexpectedly supported. The most advanced work in theoretical physics and cosmology suggests that the picture is, in important ways, correct. Time's hungry advance, driven by ever-increasing entropy, cannot be stopped or negotiated with. It is not the work of a destructive demon. It follows from mathematics whose authority has shaped the cosmos from its earliest moments and will remain in force until its final end. Entropy is embedded in the mathematics of particles and energy. It gives time its direction, its arrow. It compels us to face a future that is both inevitable and troubling, while the past remains permanently beyond reach. Around 1,500 years after St. Augustine struggled to find adequate words for time, the English industrial city of Manchester was preparing to alter it in a practical sense. In the early 19th century, towns set their clocks using local sundials. As a result, the time shown in one place could differ from that in another by as much as 30 minutes between England's western and eastern coasts. The Industrial Revolution and the expanding railway network made this patchwork of local times increasingly unworkable. A discrepancy of only a few minutes between London and another station could cause travelers to miss a train. On intersecting rail lines, it could even lead to collisions. For the first time in history, authorities decided that time itself, at least as people read it on their clocks, would be changed. In January of 1846, Manchester's residents collectively made an instant journey through time. Clocks throughout the city were moved ahead by 13 minutes, so they would agree with a standard set at the Royal Observatory in Greenwich, London. People had measured time by the sun's movement through the sky for thousands of years. Yet the demands of industry had produced something new, time made uniform. In reality, this standard time was arbitrary. It was an imagined framework imposed on the pace of modern life. The sun continued to set in Manchester 13 minutes later than it set in London, whatever the clocks in either city happened to say. Still, The steam locomotives of the Industrial Revolution did more than force societies to synchronize their clocks. They also opened a surprising path toward understanding what time may be. About 20 years before England's clocks yielded to the railway's demands, attempts to understand the engines driving these immense machines led the French engineer and physicist Sadi Carnot to a remarkably far-reaching observation. Steam power spread rapidly across an industrializing world. Those who adopted it gained prosperity and influence, even though relatively little was understood about the underlying way these engines operated. That question concerned Carnot when he wrote his influential work, Reflections on the Motive Power of Fire, in 1824. His central observation may now sound almost obvious. Heat always moves from something warmer to something colder. That is why a fireplace warms a cold room. It is why ice cubes melt in sunlight. It is also why newly formed planets, once molten, cool and solidify in the cold vacuum of space. This movement is a natural process that cannot be reversed on its own, and it is what supplies the driving power of every heat engine. With that insight, Carnot established the basis for the principle that would become known as the second law of thermodynamics. Over the century that followed, this law was developed and brought into agreement with changing physical theories. Today, it is understood that heat is not the only thing that develops in one direction. Every system moves toward a condition in which its free energy is reduced. We now describe this tendency through entropy, a mathematical measure of disorder in a system. More precisely, entropy counts the number of possible microscopic arrangements that can produce the same large-scale or macroscopic condition. A railway locomotive is an intensely ordered object. Its parts can be put together in only a very limited number of ways if the result is to remain a working engine. Its entropy, meaning its measure of disorder, is therefore low. A mound of debris in a railway scrapyard might contain the same parts as that locomotive, but when those parts lie jumbled in a chaotic heap, there are countless possible arrangements that would create essentially the same pile of scrap. Because so many configurations are possible, the heap has high entropy by definition. And more than that, left to itself for long enough, a working locomotive will eventually deteriorate into a chaotic mound of broken parts. The reverse event is so unlikely that it is effectively beyond imagination. A random heap of engine components will not suddenly sort itself out, fit together, and become a functioning train. Entropy points in one direction. In every ordinary process, systems drift toward greater disorder. Consider what happens inside the locomotive when coal burns. The fuel begins as a concentrated, organized store of energy-rich carbon. After combustion, it has been changed irreversibly into a scattered mass of lifeless ash. The useful energy that once held the fuel in that form has spread into the locomotive's boiler as heat. This basic feature of the universe explains why steam engines can operate, but its significance reaches much further. It also lies at the heart of time itself. The continual growth of entropy in the world around us gives us a practical way to tell one instant from the next. It supplies a direction to events, separating what we call the past from what we call the future. In the years just after dawn one morning, Arthur Eddington was making his way home through Cambridge. He had spent the night at the University Observatory, studying the stars, and his thoughts were still occupied by the turning points of light and the motions he was trying to understand. Near the entrance to his apartment, a stern-looking woman abruptly interrupted his concentration by stepping directly into his path. In her outstretched hand was a white feather. Its soft, delicate strands trembled in the cool morning air. Eddington understood that refusing it would be pointless, so he accepted the object with a courteous smile and walked around her. Once inside, he removed his coat, put away his hat, and placed the new feather on the steadily growing collection arranged along his mantelpiece. The year was 1917. Eddington was a Quaker and a committed pacifist, and in the eyes of much of society, that made him a coward. Yet he showed no lack of courage when confronting the deepest puzzles of the cosmos. He went on to become one of the leading authorities on gravity and relativity. In 1928, he published an ambitious book intended to make the idea of entropy understandable to ordinary readers. In it, he invited them to picture the universe's unending increase in entropy as an arrow. That arrow could point only from order toward disorder, from the past toward the future. This image helped establish what became known as the arrow of time. The arrow of time is defined by the directional change in entropy from one instant to the next. As time advances, things become more disordered, and the passage of time is marked by this relentless rise in cosmic chaos. It explains why time appears compelled to move forward, why a cause must come before its effect, and why human beings can experience time in only that direction. That is why traveling through time has become such a powerful theme in science fiction. It creates paradoxes that challenge our understanding of reality. To move into the past, a traveler would somehow have to encounter a universe in which entropy was falling rather than rising, with disordered things spontaneously becoming organized. Waves would have to retreat from the shore and rebuild themselves instead of breaking across the beach. Scattered wreckage would need to assemble itself into a working engine. Such events do not merely feel unnatural, they run against the arrow of time that governs the universe and structures our own experience. Even if a traveler could make an instantaneous jump backward and then continue living normally from that earlier point, it would become impossible to define one consistent arrow of time for the entire universe. The traveler would have moved in the opposite direction from every ordinary process, creating a conflict between personal experience and the wider progression of events. There is another route to the past suggested by the mathematics of relativity. If it were possible to move faster than light, then the strange connection between space and time would imply that the journey also carried the traveler backward through time. At least that is what the equations appear to indicate. Physical reality, however, presents a far more difficult barrier. The speed of light is among the most dependable and firmly established constants in the universe. According to Albert Einstein's equations of relativity, an object approaching the speed of light would gain mass without limit, while its length in the direction of travel would contract towards zero. Crossing that boundary would not simply require a more powerful engine, it would violate every established law of physics. Faster than light travel would also produce an extraordinary causal problem. A craft that crossed space faster than light, and therefore moved backward in time, could reach its destination before it had left its starting point. The traveler would be caught inside a causal loop, cut off from the ordinary order of events. In the universe governed by the arrow of time, an effect cannot arrive before the cause that produced it. Stephen Hawking was sufficiently confident that backward time travel could never happen that he devised an experiment around the idea. On the 28th of June 2009, he held a party and made the invitations available only on the following day. The arrangement meant that attendance would be possible only for someone capable of traveling backward in time. No guests appeared, leaving Hawking by himself with 10 bottles of champagne. Traveling toward the future is a completely different proposition. It is easy because we are doing it continuously. Every second of our lives carries us through another second of the universe. Under the right conditions, though, that journey can be accelerated. A person who ventured too close to a black hole would be exposed to gravity strong enough to distort space and time. Imagine skimming near the event horizon of a rotating black hole with roughly 8 times the mass of our Sun. Relative to companions remaining on Earth, the traveler could move into the future as much as 60,000 times faster. 17 hours on Earth could pass during a single second experienced by the traveler. The arrow of time determines which way the journey goes, but it does not prescribe one fixed rate at which every traveler must move. This one-sided character of time is sometimes called the non-symmetry of time. It is unusual because it contrasts with many other physical rules known to operate in the cosmos. Gravitational attraction, for instance, behaves the same way regardless of where or when it is observed. The basic behavior of particles in a gas provides another example. When two particles collide, they can be treated almost like tiny steel balls. They preserve their energy and speed as they strike one another and rebound. If a recording of that collision were played backward, the reversed motion would look just as physically acceptable as the original. Nothing about the individual impact would reveal which direction the film was running. The arrow of time, then, does not arise from the motions of individual particles. Those motions are governed by physical laws that work equally well in either temporal direction. The increase of entropy, and with it our experience of time passing, is not an unavoidable result that follows directly from every known law of physics. Yet it remains an unavoidable feature of the universe we actually inhabit. Bringing those two facts into agreement is still one of physics' major unsolved questions. Some thinkers have gone further and proposed that time itself may be an illusion, produced by the limited way in which human beings perceive the world. Perhaps time seems to flow because we cannot observe reality with perfect detail, seeing every part of it and every microscopic change at once. During the early 19th century, the French philosopher and physicist Pierre-Simon Laplace considered a similar possibility. He imagined an all-powerful intelligence, often described as a demon, that possessed complete knowledge of the universe. This being would know the exact location and momentum of every atom, and with that information could calculate the state of the cosmos at any moment in the future or the past. If Laplace's imagined intelligence could know all of those positions and motions, could it use them to determine what the universe would become, or reconstruct exactly what it had been? From such a viewpoint, the distinction between past, present, and future might disappear. All events would already be encoded in the complete arrangement of matter, while the apparent movement of time would reflect only our incomplete knowledge. But the arrival of quantum mechanics would make that perfect prediction far more complicated than Laplace could have anticipated. Could an all-knowing demon ever truly exist? The universe seems to offer an argument in favor of that possibility. Its natural laws are symmetrical, and in principle that symmetry appears to suggest that complete knowledge of the present could allow every past event and every future event to be calculated. Entropy and time, however, point in the opposite direction. Time becomes irreversible because energy spreads out and the amount of disorder in a system increases. Once that process is underway, it becomes impossible to make perfectly rigid predictions about everything that has happened or everything that will happen. There is another obstacle as well. At the smallest scales, nature is governed by quantum mechanics, and uncertainty and fluctuation are built into its foundations. Quantum uncertainty tells us that we cannot know the exact position and the exact speed of even one atom at the same moment. Knowing those properties for every atom in the universe is therefore far beyond reach. In fact, if such complete knowledge were possible, the statistical measure we call entropy would lose its meaning. Entropy itself would disappear, and with it, time would disappear too. Yet this still leaves a deeper question unanswered. Why does the universe have an arrow of time at all? Why is one direction different from the other? Some modern scientists have proposed that our ability to identify a direction in time comes from our cosmological closeness to the Big Bang. The idea is similar to the way the words up and down only have a clear meaning near the surface of Earth. Far from that surface, those directions are no longer quite so absolute. In the same way, our position relatively near the beginning of the universe may be what gives us a way to orient ourselves in time. If this explanation is correct, the Big Bang must have been a moment of extraordinarily unusual conditions, and the universe may still be unwinding from them nearly 14 billion years later. Ludwig Boltzmann was rarely settled in one place for long. During the latter part of the 19th century, he moved repeatedly between academic positions, working in Vienna, Graz, Heidelberg, and Berlin. In some ways, his character resembled the behavior of the atoms he spent his life studying. He was constantly in motion, full of energy that could send him unpredictably from one direction to another, from intense happiness to suicidal despair. Those dramatic changes in mood did not stop his scientific work. Boltzmann was far ahead of his time in imagining the world as a collection of atoms. He helped establish an entirely new branch of science, statistical mechanics, which provided a framework for understanding the relentless increase of entropy. To picture his argument in a simple way, imagine particles colliding like balls on a billiard table. If we know the speed and angle of each impact, then the physics and geometry of an individual collision can be predicted. The ordinary laws of nature still apply. But as collision follows collision, the arrangement of the balls on the table becomes more and more disordered. It becomes increasingly improbable that the particles will keep producing some neat, organized pattern. Such a result is not impossible. It might happen once by chance, but for the system to move continually in the direction opposite to time, the same extraordinarily unlikely event would have to keep occurring again and again. The odds quickly become overwhelming. From this, Boltzmann argued that the second law of thermodynamics, and therefore the arrow of time itself, was a statistical necessity. Disordered arrangements are vastly more numerous and more likely than ordered arrangements. Even in a universe ruled by natural laws that are indifferent and symmetrical, disorder should normally win simply because there are so many more ways for it to exist. Boltzmann faced relentless criticism over his mathematical account of physical existence. Tragically, he died by suicide before later evidence could establish that his theories were correct. Today, we can imagine the universe as an enormous billiard table, perhaps an infinite one. The continuous rise of entropy, which gives time its direction, suggests that the cosmos is still relatively close to the opening moments of the game. If randomness is still statistically increasing, then the universe must have begun in a state with a greater degree of order. That conclusion seems strange when we picture the earliest cosmos. According to our understanding of its first moments, the universe was a nearly uniform soup of protons and raw energy. At first glance, that sounds far more random and disorganized than the stars, galaxies, planets, and human beings that exist today. How could a smooth, uniform universe have lower entropy than the richly structured universe around us now? It is possible to calculate the entropy of both the early universe and the universe we observe today by using what is known as the Boltzmann constant. At the time of the Big Bang, the entropy of the compressed, radiation-filled infant universe was certainly not zero or even especially small. Its value was 10 to the power of 88 multiplied by the Boltzmann constant. In other words, it could be represented as a 1 followed by 88 zeros. The entropy of the universe today is represented by a 1 followed by 103 zeros. That is some quadrillion times greater than the earlier figure. So the universe has indeed undergone a huge increase in entropy, but its initial value was not as low as our first impression might suggest. There is an additional surprise. The forms of order that human beings notice so readily have almost no effect on the total entropy of the universe. The appearance of stars, galaxies, worlds, and life may be enormously important to us, but on the cosmic scale, those structures barely change the overall accounting. Even 14 billion years have made very little difference to the entropy of the background radiation that has existed since the beginning. The entropy of the cosmos has risen by a factor of roughly a quadrillion because one particular kind of structure has been added: black holes. These mysterious objects sit at the centers of galaxies, while others remain hidden throughout the wider universe. They form when enormous quantities of matter are compressed into a very small region. A black hole contains so much matter, and therefore so many particles, that there are almost limitless ways to rearrange those particles while still producing the same massive, lightless whole in space. That enormous number of possible internal arrangements is enough to make black holes dominate the entropy of the universe. The black hole at the center of the Milky Way alone has an entropy 1,000 times greater than the entropy of the entire universe shortly after the Big Bang. As time passes, gravity will continue to create more black holes and enlarge the ones that already exist. Their growth will push the entropy of the cosmos ever higher, carrying the arrow of time forward with relentless force. But this process will not continue forever, at least not in the way you may expect. The heat death of the universe will eventually leave all energy spread evenly across an almost infinite expanse of space. For now, entropy is still increasing within black holes, and the disorder of the universe as a whole is still gradually rising as time moves forward. But trillions of years from now, the black holes will have swallowed every remaining particle in the cosmos. Eventually, those black holes will evaporate as well. Nothing can endure through that unavoidable final stage. Once matter and energy have vanished into a completely even distribution, the total entropy of the universe will be as high as it can possibly become. The result will be a kind of universal white noise, pure randomness in a state of ultimate equilibrium. Because time cannot run backward, that condition will remain unchanged forever. With no differences left to develop and no events left to separate one moment from another, time will no longer have any practical meaning. This would be the true end of time, a cold, dark, empty universe existing beyond space as we understand them. But it would be a mistake to assume that the story must end there, because nothing needs to happen in this vast, empty universe. Entropy may already have reached its highest possible value, but that does not mean that every particle is locked into one permanent arrangement. It means there are almost endlessly many ways for the contents of the universe to be distributed. The physical material that remains can still wander through those random arrangements, so even an entropic equilibrium is not completely motionless. It is a dynamic equilibrium. The universe as a whole may never become more organized, yet probability allows small, temporary islands of order to appear within it. Imagine tossing 100 coins. The odds of every coin landing on tails are incredibly small, but they are not zero. In a universe that has reached its most random state and can continue for effectively unlimited time, there will be opportunity after opportunity for random events to produce almost any result that can be imagined. The modern physicist Sean Carroll has used this principle to propose one possible story for the origin of our cosmos. Picture a universe that has already lived through its entire history and reached its entropic end. Billions upon billions of years ago, it would have settled into the condition of a parent universe, unchanging on the largest scale, without a meaningful passage of time, but still subject to tiny local fluctuations in entropy. One of those fluctuations might, by chance, arrange energy in an extraordinarily unusual way. It could gather that energy into a highly compressed region with an inexplicably low level of entropy. In a figurative sense, this would be a newborn universe whose billiard balls had already been placed on the table, waiting for the first movement of the game. Carroll suggests that such a fluctuation could mark the beginning of our Big Bang, and with it, the beginning of our own arrow of time. Our universe in this picture would have emerged as a brief disturbance or hiccup in a parent cosmos that otherwise had no direction through time. The idea is appealing, and it seems to fit comfortably beside certain cyclical accounts of cosmic origins. But it also leads to an unsettling possibility. If an old parent universe can generate an entirely new universe, then its limitless sequence of random events can also produce nearly anything else we might imagine. That includes additional observers or versions of ourselves. A complete universe requires an enormous number of random arrangements. A new copy of a person requires far fewer. More precisely, the result could be a human brain without a body, drifting alone through space. This hypothetical object is known as a Boltzmann brain, a name inspired by the work of Ludwig Boltzmann. It belongs to a thought experiment that hangs over theories involving an eternal universe at maximum entropy. At first glance, the notion seems absurdly unlikely. How could a cold, empty cosmos suddenly produce a brain containing thoughts, artificial sensations, and apparent memories? Yet that brain is still one of the possible arrangements available to a maximally disordered universe. Given enough time, even a permutation that appears impossible can occur spontaneously. With still more time, the same event could happen again, and then again. If the universe truly continues forever after reaching its entropic end, Boltzmann brains become unavoidable in the statistical sense. Their individual appearances would be fantastically rare, but eternity provides an unlimited number of opportunities for rare events to occur. In fact, the comparison becomes even more disturbing when we look only at probability. Human beings with physical bodies living in the actual universe when it is nearly 14 billion years old are vastly less probable than isolated Boltzmann brains appearing in an empty universe that has been cycling through random arrangements for hundreds of trillions of years. Creating an entire cosmic history, complete with stars, planets, bodies, and observers, demands far more special conditions than producing a single brain with an internally consistent set of experiences. The statistical implication follows harshly. Our thoughts and memories could be more likely to be the illusion of an invented universe imagined by disembodied Boltzmann brains than genuine reflections of a cosmos that is still close to its birth. In that scenario, the world around us would feel real only because the random brain would contain memories and sensations arranged to make it seem real. Physicists, of course, do not take this as a literal description of our situation. The problem is a warning sign within the theory, not evidence that we are actually bodiless brains floating through darkness. Modern cosmology seeks an explanation that does not undermine the existence of observers like us, and does not leave eternity filled with dreaming minds that merely imagine a universe. If we are genuinely here, experiencing a universe that is nearly 14 billion years old, then the idea of an everlasting cosmos remaining in timeless stasis must be incomplete or mistaken. A satisfactory theory would need to give space-time a definite end before random statistics have enough opportunity to produce so many Boltzmann brains that they outnumber ordinary observers like us. Several possibilities are being explored at the farthest edge of theoretical physics. Perhaps the universe will eventually contract, leading to a big crunch followed by another beginning. Perhaps collisions between higher dimensional structures, as suggested in some versions of string theory, could erase the universe before such statistical problems arise. None of these ideas has settled the issue. The search continues because the alternative leaves the foundations of our experience in a deeply unstable position. St. Augustine could not have known how accurately his words would echo through modern cosmology when he said that time resists definition. Arthur Eddington could describe the arrow of time, but describing its direction was not the same as understanding what time truly is. Ludwig Boltzmann, despite all the brilliance and personal difficulty surrounding his work, gave physics a statistical demon that still threatens the reliability of our picture of reality. Even now, physicists have no definitive account of what ultimately began time or what will finally bring it to an end. That uncertainty raises a grim possibility. Perhaps all of those influential thinkers were only minds, drifting without bodies through the emptiness, dreaming of a universe they could almost comprehend. Or perhaps our recollection of those scholars is itself a fabrication, assembled by one solitary Boltzmann brain wandering through an eternal universe without time. There is another possibility. Theoretical physics may eventually discover the answers we are looking for. For the sake of the reality we experience, the only thing we can do is hope that those answers arrive.